Today we're going to talk about limits at infinity. Limits at infinity. I'm referring to something like lim x goes to, usually you put a number here. Today we're going to talk about what if you put infinity or perhaps minus infinity right there. What does this mean? Lim as x goes to infinity of f of x. It does mean something. Let's try not to talk about exactly what does infinity mean. Infinity as a concept is, everybody kind of knows what it means, but it's also kind of mysterious. You don't have to wonder about the mysteries of the universe to talk about the limit as x goes to infinity of f of x. What does it mean? How about an example? Let's look at lim x goes to infinity of x plus 4 over x minus 1. All right, this is a function. When I say lim x goes to infinity, if you graph this function, let's just talk about on the picture first, is easier to deal with than looking at the formulas. On the graph of this function, if you graph it, you will see there's a vertical asymptote at 1. That's because this is where the denominator becomes 0. And there's a horizontal asymptote of this function at y equals 1. And the function, the values sort of fit in like this. All right. What do you say? What is the limit as x goes to infinity? What this means is, what is the y value that this function approaches when the x goes out that way forever? When the x value increases without bound, what is the y value approach? And if you believe this picture here, as the x value goes out to the right forever, the y value will approach y equals 1, right? That's sort of the meaning of this asymptote. This line goes towards this y value, y equals 1. So in this example, it is 1. And the interpretation of this, what this means, well, you could just say it this way, is that this function, x plus 4 over x minus 1, has a horizontal asymptote. Has a horizontal asymptote at y equals 1. All right, this is what it means when I say x goes to the limit as x goes to infinity of f of x equals 1. It has a horizontal asymptote at y equals 1. Can I just say as x goes very large? Really, there are two possible horizontal. You could have a horizontal asymptote going this way, and you could also have a horizontal asymptote going this way. And actually, in this example, we have both, and they are the same horizontal asymptote. It's possible to have different values, but as x goes very large, this one has a horizontal asymptote at y equals 1. That's all I'm saying when I say this, lim x goes to infinity. It means when the x values are super, super big, that way, then the y values approach 1. And you can also talk about lim as x goes to minus infinity. That means when the x values are super big, but in the negative direction, the y values approach something or other. All right. This is how you can identify them on a picture by looking for horizontal asymptotes. What about, how do I identify these? Looking at equations. With the equations is a little more interesting. Before we talk about equations in general, I got some very basic properties of these limits. It is a fact that if you do the limit as x goes to infinity of 1 over x, I'll say 1 over x to the n, 1 over any power of x, where n is positive. If n is negative, then remember a negative exponent indicates 1 over something. Here I already have 1 over something. If this were a negative exponent, it actually wouldn't be, you wouldn't write it in this way. So assuming that this n is an ordinary positive exponent, this limit equals 0. Think about this. We're asking about what happens to this value, 1 over x to the n, when the x itself is growing very, very large. Well, if x is very large, then you're going to have this denominator will be very, very large because you're taking x to some power. But the numerator is just 1. You're looking at 1 divided by some super big number. In the limit, this limit will be 0, right? As this x approaches, or as this x grows forever, the y value as the x continues to grow will approach 0. All right? This is what I say, the basic rule. That's the first basic rule. And the other is just the other way around. Limit as x goes to minus infinity, 1 over x to the n. is also 0 for the same reason. The only difference is this time x is super big but negative. But it's the same. If you divide 1 divided by some super big negative number, you're still going to get something which tends to 0 as x grows without bound. So, and this is also when n is positive. If n is negative, then you wouldn't have written it this way, and it's different. All right, there you go. Moral of the story, when you have powers of x in the denominator and you take this limit, you're going to get 0 for at least for those parts of the formula. So you can sort of use this in some larger examples. Here's an example. What if we do lim x goes to infinity of, how about 2 over x to the 8 plus 7 over x plus 5. Now, when you do a limit like this, you really just look at each individual part here and you see what is this limit approach, what is this limit approach, and what is this limit approach. And each of these two, they fit this format, right? This one is like 1 over x to the 8. Now, it's 2 over x to the 8, but that doesn't matter. You're going to get 0. If you multiply by 2, you're still going to get 0. So this limit here, when we do the limit of these guys, I'm going to get 0 here. And then another 0 here. 7 divided by x is the same as this, where the n is a 1, right? The power on the x is just a 1. And then this 5, there's no x there at all. So this is just going to stay equal to 5. Even if x gets very large, this part of it will still equal 5. Anyway, the answer then is 5, right? So the limit of this thing is 5. This is a pretty specific example. Big whoop. I want to talk about some more interesting things than that. Before we do, let me just add on to these basic rules. Sorry, I should have told you this before. I'm going to give you 2 more basic rules. I suppose you could make their own, make another, you know, more basic rules. This is about if x is in the denominator. What if x is not in the denominator? What if you're just looking at, say, lim x goes to infinity of x to the n, not in the denominator, just hanging out all by itself? You got to ask yourself, if x is becoming very, very large, then what y value will this approach as the x continues to get larger? And the answer is this will not approach any y value. If this x continues to get very large, then x to the n will also continue to get very large and will not eventually stabilize at any value, right? As the x goes to infinity, this is also going to go to infinity, I suppose. But I'm just going to say this limit does not exist. And also, same goes for minus infinity, right? This limit does not exist. So when you're talking about limits at infinity, that's the topic for today. That is x goes to infinity or x goes to minus infinity. If x is in the denominator, you're going to get 0. If x is in the numerator or by itself, you're gonna the limit does not exist. Okay. What about some combination of these? Like if the x is, if there's some big thing and like the x is in the numerator sometimes and in the denominator some other times. That's more interesting. Let's talk about an example like that. How about, actually let's look at that first example that I mentioned. Lim x goes to infinity of x plus 4 over x minus 1. Remember this one? This I said, you know, at the very beginning, right? Cast your mind back 10 minutes ago. I don't know how long that was. Can we do this without looking at the graph? Remember, if you look at the graph, the answer was 1, right? But let's see if we can sort of figure this out without looking at the graph. There's a trick for this. The trick, you know, what's weird about this is you have x's in the numerator and also in the denominator. The trick is send every x into a denominator of some sort. So the trick here is going to be divide through by the biggest power of x that you see anywhere. I wrote biggest. By the biggest power of x. And in this particular example is just x to the 1, right? All I see is just x. There are no larger powers of x in the formula. But anyway, that's what I'm going to do. I'm going to rewrite this, but divide everything through by, in this case, x to the 1. So I still have this lim here because I didn't do that part yet. And I'm going to divide everything by x. So I write x over x plus 4 over x divided by x over x minus 1 over x, right? And what do you get? I can simplify these. Of course, x over x is just 1. So I got 1 plus 4 over x. I'm going to leave like that. then 1 minus 1 over x. All right? Come on now. All right, what can we do with this? Now, using your basic facts from before, we said before, when you have the limit as x goes to infinity and x's are in denominators, then those things go to 0. So this right here and this right here will both become 0 when we take the limit. What about these? Well, they're just 1. They don't change at all when we take the limit. Because they don't involve x's at all. So when I take this limit as x goes to infinity, these parts become 0 because of the basic facts that I told you before. Anyway, what this amounts to is 1 plus 0 over 1 minus 0, right? These parts became zeros. And the answer is 1, which is the answer that we saw on the graph at the beginning. So if you didn't believe me back then, I hope you believe me now. The limit here really is 1, and you can figure it out pretty easily without looking at the graph. All right, let's just do some more examples of the same type. This is really all I wanted to talk about today, so we're just going to do a few more. Let's try another one. How about lim x goes to infinity, x squared minus 3x divided by x to the 5 plus 4x minus 1. All right, let's try that one. Again, the basic idea is I'm going to divide through by the highest power of x that I see anywhere. And in this example, that would be x to the 5. So this I'm going to rewrite. Dividing through by x to the 5 everywhere. I get x squared over x to the 5 minus 3x over x to the 5 divided by x to the 5 over x to the 5 plus 4x over x to the 5 minus 1 over x to the 5. All right? What now? Now we can cancel a bunch of x's. So x squared over x to the 5 is the same as 1 over x cubed, right? Minus 3x over x to the 5. I cancel one of the x's. I get 3 over x to the 4. Right? Here, x to the 5 over x to the 5 is 1. Here, 4x over x to the 5. I cancel 1x. I get 4 over x to the 4. And here, can't cancel anything with that one, right? And now, we gonna use the basic fact. Remember, the basic fact said this limit when x goes to infinity, anywhere where you see x's in the denominators will become 0. That means this one, this one, this one, this one, they all become 0 when we take this limit. And so, the answer after doing this limit, these parts become 0, and what's left over is 0 minus 0 divided by 1 plus 0 minus 0. And this is 0, right? This, if you simplify, is just 0 divided by 1, and 0 divided by anything is 0. Right? Hope you don't mind. 0 in the top is fine. 0 in the bottom is a big problem. 0 in the denominator. But 0 in the numerator, no problem. You just get 0 as the answer. All right, so this limit ended up being 0. Would you mind if we have a little introspection here? Let's think a little bit about what happened in this problem. Everything ended up being 0. Ask yourself, like, what about the original formula here contributed to this answer? For example, did this 4 really matter? Like, if this had been, instead of a 4, if it had been a 5, would that change anything? The answer is no. There would have been a 5 here, a 5 here, but it would have turned into 0 here anyway. All right? Did anything else matter? Really, all that mattered is the numerator, both parts of the numerator ended up becoming 0. And the reason that that happened is because when I divided out by this power, this x to the 5 was a bigger power than anything up here, and so it caused everything in the top to like have these denominators in them, which caused everything in the top to become 0. So can I just say this happens whenever if these are polynomials. I hope you remember the word degree of a polynomial. The degree is the highest power that you see anywhere in the polynomial. So on the top, we have a polynomial of degree 2, because this is 2. And on the bottom, we have a polynomial of degree 5. And this exact same thing will happen whenever the degree on the bottom is greater. So this happens whenever the degree on the bottom is greater than on the top, right? The reason that this everything turned into zeros at the end is because this x to the 5 was more than this x to the 2. So that when I divide everything out by x to the 5, everything ended up having these little denominators which became 0. So this happens whenever the degree on the bottom is greater than the degree on top. This actually means whenever you see something like this, if you look at the 2 degrees and the one on the bottom is greater, you can immediately conclude that the limit is 0. This is a pretty sweet trick because it allows you to just skip all of these intermediate steps. Can we look at what happens if it's the other way around? What if the degree on top is bigger than the degree on bottom? Let's try it. All right, here's an example where the degree on the top is bigger than the degree on the bottom. Let's see what happens in such a case. Again, your strategy is simply to divide through by the highest power of x that you see anywhere, which in this case would be x to the 4. So let's divide everything through by x to the 4. I get 3x to the 4 over x to the 4 minus 7 over x to the 4 divided by 8x cubed over x to the 4 minus 100 over x to the 4. And what happens here? We can cancel like we did before. Lim x goes to infinity. Okay, 3x to the 4 over x to the 4 is just 3. Here, you can't do anything with that. 7 over x to the 4. Downstairs, this is going to go 8 over x. And this one, I can't do anything with that. All right, what happens when I take the limit of these guys? Again, taking the limit as x goes to infinity, anything which has x's in the bottom is going to become 0. That would be this, this, and this. All right, so all of these things become 0, and the answer just is 3 minus 0 divided by 0 minus 0, which is 3 over 0. Now, denominator being 0 is not allowed, so you need some interpretation of this. What does this mean? Well, just like we saw last time, if you are taking the limit of something and you end up with a constant on the top divided by a 0 on the bottom, where the top is not also 0, but some non-zero divided by 0, that means, what does that mean about the limit? It means the limit does not exist. All right? So in this example, the limit does not exist. And I want to ask you again to think about what exactly contributed to the answer here of does not exist. Like, was it because this number 100 had something to do with it? No, actually, this number 100 ended up being totally irrelevant because it turned into a 0 anyway at this step. The only reason that I got this D and E for the answer is because the degree on top is bigger than the degree on the bottom. That means when I divide it out by the biggest power of x, the top of this did not become 0, but everything on the bottom of this did become 0, and that causes the limit to not exist. So whenever the degree on the top is bigger, put this in a little box. I'm going to do a little summary at the end about this, but when the degree on top is bigger, the limit does not exist. All right? So the thing we said before was when the degree on the bottom is bigger, the limit equals 0. Now I'm saying when the degree on the top is bigger, the limit does not exist. What if the 2 degrees are equal? That's the only other situation. Let's try one of those. All right, how about this one? Here we have the degree on the top and the bottom are the same. They are both degree 4, all right? Let's see if we can do the same idea. I'm going to divide out by the largest power of x, which is x to the 4. So it becomes 3x to the 4 over x to the 4 minus 8x over x to the 4 divided by 7x to the 4 over x to the 4 plus x squared over x to the 4 minus 3 over x to the 4. We simplify where we can. Here I get 3, just 3. Here we have minus 8 over x to the 3rd. Here we have just 7. Here we have 1 over x squared. And here 9 minus 3 over x to the 4. And now when I take this limit, again, the things which have x's on the bottoms are going to turn to 0. So these 3 parts will become 0. And what remains is 3 minus 0 over 7 plus 0 minus 0. 3 over 7. All right, we got like an actual answer here. In the other 2 categories, the answer was always either 0 or does not exist. Here we got some, more interesting number. Can you identify where this number came from up here? I think you can. This number is the fraction that you get by looking at the coefficients of the highest degree terms. All this other stuff didn't matter at all because it turned into zeros at the end. So in the case when the degrees are equal, this will be the answer. It will be the ratio of the highest degree term on the top and on the bottom. So I'm going to try and summarize. These are like three categories that gives you the ultimate trick. If you know this trick, you can do any of these examples just immediately without any work to it. So I'm going to write this like a theorem. Theorem, you know, is a math word just for a fact that is true. Generally, theorem means a fact that you can prove that it's true. And it's typically like a useful or interesting fact. This is a pretty sweet trick. It's a lit trick. I think the young people these days, they use the word lit. This trick is lit, yo. Yeah, okay, so if we have lim x goes to infinity of p of x divided by q of x, where p and q are polynomials. That's the kind of thing that we've been talking about this whole time. Polynomials. Sorry. If we're looking at the limit as x goes to infinity of a fraction involving a polynomial on the top and a polynomial on the bottom, then you can tell the answer immediately. You don't have to go through all this work because you know the lit trick. Then if the degree, I'll just write deg for degree, if the degree of p of x is greater than the degree of q of x, then the limit as x goes to infinity p over q, p of x over q of x. If the degree on top is bigger, then the limit does not exist. If the degree of p of x is less than the degree of q of x, then this limit equals 0, and if the degrees are equal, then the limit x goes to infinity p of x over q of x is the ratio of the top degree coefficients. You take the coefficient on the top and you divide it by the coefficient on the bottom. This is sort of in 3 parts. This covers all possibilities if you're talking about limit as x goes to infinity of p of x divided by q of x. This is the lit trick for finding the limit as x goes to infinity. And it's even more lit than that. Can I write one last thing on the bottom? I don't know if it'll fit. I'll write it over here. Same for limit as x goes to minus infinity. Now this is not something that we talked about much, but all of these are based on some level on those basic rules that I said at the beginning. If you take a limit of 1 over x to the n, you get 0, right? But those are true for x going to positive infinity and also for x going to minus infinity. So if you're looking at, rather than limit x goes to infinity, if you're looking at x goes to minus infinity, exactly the same business applies. You make no modifications to the answer. The fact that it's going to plus infinity or minus infinity doesn't matter at all. All right? If you're doing these problems on a test or on a homework or something, I will expect you basically to show no work because you can immediately say what the answer is just by looking at the degrees. Let's just do a bunch of them. You can answer these faster than I can write them. All right, I guess I wrote those pretty quickly, but now that you see them, you should be able to answer any of them immediately. You don't have to do any work for this. all you care about is the degree on the top versus the degree on the bottom, and you remember your lit tricks from before. So this one here, limit as x goes to infinity, 8x squared minus 3x over x to the 10. You look at the degrees on the top and the bottom. On the top is degree 2, on the bottom is degree 10. The degree on the bottom is bigger. Remembering your trick, that means the answer is 0. All right? How about this one here? Again, all you look at is the degrees. In this case, the degree on top is 2. The degree on bottom is 1. And so the degree on the top is bigger. And so this limit does not exist. All right? Because the degree on the top is bigger. How about this one? In this case, the degrees are the same. Degree 4 on top, degree 4 on the bottom. In this case, that means you get the ratio of the leading coefficients, the ratio of the top degree coefficients. In the top, it would be the 8, and on the bottom, it would be the 7. You get 8 over 7. That's all there is to it. How about this one here? 3x plus 4 over 8x squared minus 1. By the way, did you notice this was a plus infinity, this was a minus infinity, this was a plus infinity? It don't matter. It has to be infinity. If it's not infinity, then you got to do something like we did last time. These tricks are only apply for limits when x is going to infinity or minus infinity. Let's just do these ones. They're not any harder. Here, the degree on the bottom is bigger, and so the limit equals 0. Here, what about the degrees? This is a tricky one. I tried to trick you. Did you get tricked? Did I get you? I tried to trick you because I wrote the 4x to the 4 over here. So what are the degrees? The degree here is 4, even though I didn't write it at the beginning. It doesn't matter what order you write them in. You're just looking for the highest power of x. Here, the degree is 4. On the bottom, the degree is also 4. And so I get the ratio of the coefficients, this one and this one. The answer is 3/2, right? Those are the ratios of the highest degree terms. And how about this one? This one looks kind of crazy. It don't matter, though. I've said x to the pi. How you like that? Pi is a number, of course, it's a little bit more than 3. So the degree of, I guess, the degree on top is pi. Which has a bigger degree? The degree on bottom is 2. The degree on top is pi. Pi is more than 2 because pi is like close to 3. So the degree on top is bigger, which means the limit does not exist. All right? More of the story, if you know the lit tricks, then these are very, very easy.